Hello class, today we are going over our squares and square roots readiness guide. So the first thing we did in this unit was some definitions, and this is a primarily definition-based unit. So we're first asked to use 4 definitions to explain why 16 is a perfect square and what the square root of that would be. And of course we have our definition in words, we have ability to represent squares on diagrams, we have powers, which is a new idea, and we have the idea of factors. What about factors would make something a perfect square? So in words, a perfect square is a number that's made by multiplying another whole number by itself. So we can say that 16 is a perfect square because it can be made by multiplying the whole number 4 by itself. Obviously, 4 times 4 is what would give us 16. In terms of a diagram, our perfect square should be the area, so the number of tiles that we use. And if it's a perfect square, squares, of course, have equal side lengths. So if we represent an area of 16, we can start by shading in or selecting the first square. Obviously, that's an area of 1. If we go out another even layer, that's an area of 4 that's used up. We want to get up to 16, so we'll go to another layer. 5, 6, 7, 8, 9 is the third layer. Still not 16, so we'll go one more layer, and we'll go 10, 11, 12, 13, 14, 15, 16. And of course, this is now a square shape. We know it's a square because it has equal side lengths of 4 units around the outside. So we can go ahead and say an area of 16 can be arranged into equal sides of 4. In terms of a power means to represent a number using an exponent. In this case, we can say our 16 is equal to 4 times 4. And 4 times 4 is 2 factors of 4 multiplied together. So we can represent that using a base of 4. What are we multiplying? An exponent of 2. How many factors of 4 are we multiplying? We're multiplying 2 factors of 4. So this is our power here together, our base and our exponent, multiplying 2 factors of 4 together. And then in terms of factors themselves, we can say that 16 breaks down into 2 and 8, which breaks down into 2 and 4, which breaks down into 2 and 2. And our key idea here is we want to be able to sort those factors into 2 equal groups. So in terms of 16, we can say it's equal to our red group, 2 times 2, multiplied by our blue group, which is also 2 times 2, and this is 2 equal groups of factors. Now, in terms of our square root in all of these cases, our square root is going to be the number that multiplies by itself to make the perfect square 16. So in our basic definition, 4 is our square root. Because it's the number that's multiplying by itself to make 16. In our diagram, again 4 obviously, but that's your sides of your diagram are the square root, while the area is the perfect square. In a power, it's the base that is your square root, and then in your factors, one of your groups of factors, which 2 times 2 obviously gives you 4, is your square root. In terms of stating each value, of course, these ones here are primarily from memory. Now, if you did forget any of these, you could work them out by hand. So, for example, 18 squared is 18 times 18. And since elementary school, we know how to long multiply. So 8 times 8 is 64. 8 times 1 is 8, plus 6 is 14. Placeholder 0. 1 times 8 is 8, and 1 times 1 is 1. Add them up. 4, 12, carry 1, 3. So 18 squared is 324. But of course, that is one of our memorized lists since we go between 1 and 20 for our square roots, and by tens. and then obviously that creates perfect squares 1 through 400. So 13 squared is a memorized one, 169. 144 is made by multiplying 12 by itself. So your square root symbol here asks you, what would you multiply by yourself to make 144? That is 12. What would you multiply by itself to make 64? That's 8. 40 squared is 4 squared with 2 zeros at the end. So 4 squared is 16, 2 zeros is 1600. 361 is made by 19 times itself. 14 squared is 196 from memory. 16 squared is 256 from memory. What number makes 16 when it's multiplied by itself? That is 4. Square root of 256, what number makes 256 when it's multiplied by itself? That's 16. 19 times 19 is 361. And then last one here, definition, our square and our root cancel out, leaving us with just 225. Okay. In terms of determining if each number is a perfect square, we want our perfect squares to be able to be sorted into 2 equal groups. So if we go through just like we did in class and we circle every second factor, as long as our factors are in order, of course, our first group is going to be 3 times 3 times 7. And our second group is going to be 3 times 3 times 7 as well. Okay, so since we can sort them into 2 equal groups, we're going to say yes. 3969 is a perfect square because factors can be sorted into 2 equal groups. That's our main idea definition for factors. Okay, if we take a look at our question B, we try the trick again. So we're going to circle every second factor of each type. So here I have, that's every second one as it is. We go ahead and we look at those. We've got 3 times 3 times 5, and our other group 3 times 7 times 7. Okay, so when we look at this, we've got an odd amount of factor 3. That's not going to be able to be sorted into 2 equal groups. We could put a 1, 7 in each group, so if we rearrange those, that could happen. But we've also got only 1, 5, so that's not going to be able to be equally sorted into 2 groups. So I'm going to say no. 6615 is not a perfect square because its factors cannot be sorted into 2 equal groups. In terms of our square roots here, we know that if we can sort our factors into 2 equal groups, the value of the square root will be the value of one of those groups. Of course, your square root tells you what is multiplied by itself. You're multiplying 2 equal groups by itself. The value of one of those groups is the thing that's being multiplied by itself. So let's go ahead, just like we did in class, sort every second factor. So we got our square root of our 2 groups, 2 times 5 in the red group, and 2 times 5 in the blue group. Remember, the order of multiplication does not matter. And since we have something multiplied by itself under that square root, the value of one of those groups is our value of our square root, so it's 10. Let's do the same thing over here. Again, we want to be careful with selecting every second factor. So the first 2 can go in the first group, and the second group, 2 can go in the second group. The first 4 can go in the first group. The second 4, can go in the second group. And the first 5, I don't know why I'm using green there. First 5 can go in the red group, there we go. And the last 5 can go in the blue group. And of course, this is still being square rooted. So our square root says what's being multiplied by itself, and we have 2 times 4 times 5 being multiplied by itself. 2 times 4 is 8, times 5 is 40. So the value of our square root is the value of one of our groups, which is 40. In terms of question C, we can go ahead and break down our numbers here into their factors. So 2 squared is 2 factors of 2 multiplied by themselves. 7 squared is 2 factors of 7. And 25 squared, well, it's not squared, but 25 is made by 5 times 5. So just breaking down that 25 into its factors. Again, we're going to go ahead and circle every second factor of each type. And that gives us our 2 equal groups. So 2 times 7 times 5 in the red group, and 2 times 7 times 5 in the blue group. And since our square root asks us what's being multiplied by itself, one of these groups is being multiplied by itself. So 2 times 7 is 14, times 5 is 70. Last one here, we just have a calculation. We know in a calculation with more than one operation, we follow bedmass order. So 10 squared is 100, 9 squared is 81, and the square root of 289 is also an exponent, so that is going to be done before the addition or subtraction. 289 is made from, 17 multiplied by itself, so the square root of 289 is just 17. Now we're going to calculate in bedmass order, so 10 take away 81 is 19, and 19 plus 17 gives us an answer of 26. 36. That's better. Okay, to use prime factorization to find each square root, we want to start by breaking down our numbers into its prime factors. Prime numbers are 2, 3, 5, 7, 11, 13, so on and so forth. And we can use our grade 7 divisibility rules to help us with this. So I'm going to start by breaking down 1024. And remember, you can use long division as well to help you with this if you're not sure what you get when you do your division. I do know that 1024 is even, so it will divide by 2. Let's just do that one here in case you weren't sure what that is when you divide. 2 goes into 1 0 times, 2 goes into 10 5 times, creating 10 exactly. 2 goes into 2 1 time, creating 2 exactly. And 2 goes into 4 2 times, leaving a remainder of 0. So we can say that, first off, 1024 is equal to 2 times 512. 512 is still even, so we're still going to divide it by 2. 2 goes into 5 2 times, creating 4. That leaves us with 1 1. So 2 goes into 11 5 times, leaving us with 1. And 2 goes into 12 6 times. Now, if we were just doing a factor tree, you could recognize the perfect square 256 and break it down into its 2 equal factors. But we do want prime factors, so we're going to continue dividing by 2. 256 divided by 2, 2 goes into 2 1 time, 2 goes into 5 2 times, 2 goes into 16 8 times. Still even, so we're still going to divide by 2. 2 goes into 1 0 times, 2 goes into 12 6 times exactly, and 2 goes into 8 4 times. Still even. 2 goes into 6 3 times, and 2 goes into 4 2 times. Still even. 16 8 4 and 2's. Okay, so now that we have our prime factor tree, we can go ahead and select every second factor to form our 2 equal groups. So for our red group, we've got 2 times 2 times 2 times 2 times 2 again. And same for the blue group, 5 factors of 2. Now the value of our square root will be the value of one of these groups. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we can say the square root of 1024 is 32, the value of one of our groups of prime factors. Let's move this little guy over here. Okay. For 676, same idea. We're going to start by breaking down 676. 676 is even, so it divides by 2. 2 goes into 6 3 times, 2 goes into 7 3 times as well, leaving us with 1, and 2 goes into 16 8 times. That's still even, so we'll divide it by 2 again. 2 goes into 3 1 time, 2 goes into 13 6 times, and 2 goes into 18 9 times. Okay, 169 is a perfect square, and in this case we do need to recognize that because it is the perfect square of the prime number 13. So that's going to be as simple as we can break down that into prime factors. Then we're going to form our 2 equal groups by selecting every second one. and our red group is going to be 2 times 13. Our blue group also 2 times 13. Since your square root answers what number is multiplied by itself, and this group is multiplied by itself, we've got 2 times 13 gives us 26 as our square root. So we can say square root 676 is equal to just 26. And same thing in our last one. Again, 7,056 is even, so I'm going to start by dividing it by 2. 2 goes into 7 3 times, leaving us with 1. 2 goes into 10 5 times. 2 goes into 5 2 times, leaving us with 1. And 2 goes into 16 8 times. Let's continue dividing by 2. 2 goes into 3 1 time. 2 goes into 15 7 times, leaving us with 1. 2 goes into 12 6 times, and 2 goes into 8 4 times. Still even, so we'll still divide by 2. So 2 goes into 1 0 times. 2 goes into 17 8 times, leaving us with 1. 2 goes into 16 8 times exactly, and 2 goes into 4 twice. Still even, so we'll divide it by 2 again. 4 4 and 1. Now this does not divide by 2, but by adding up the digits 4 plus 1, we get 9. And our divisibility rule for 3 is that the sum of the digits must divide by 3. So 4 plus 1 is 9. 9 does divide by 3, so this number divides by 3. Let's do that. 3 goes into 4 1 time. 3 goes into 14 4 times, which would make 12, leaving us with 2. And 3 goes into 21 7 times. Again, let's add up our digits. 1 plus 4 is 5, plus 7 is 12. 12 does divide by 3, so this number divides by 3. Let's do that. 3 goes into 1 0 times. 3 goes into 14 4 times, leaving us with 27. And 3 goes into 27 9 times. And we'll finish off by recognizing that 49 is 7 times 7 in its prime factors. Again, let's sort those. So we're going to select every second one. We'll make our 2 groups. I might do that over here. Oops, that a bit smaller. So our red group is going to be 2 times 2 times 3 times 7. And same with our blue group. I might have to move that over a bit. Let's add some dividing lines here. Yeehaw. And our blue group as well. 2 times 2 times 3 times 7. Since we're square rooting all of this, we want to know the value of one of those groups since it is multiplied by itself. 2 times 2 is 4, times 3 is 12, times 7 is 84. So the value of our square root is 84. Okay. On the back page, we are estimating our square roots. First thing we need to do when we are estimating our square roots is to identify the perfect squares on either side of our desired number. So for 12, the smaller perfect square is 9, and the larger perfect square is 16. And of course, in terms of 12, it's 3 away from 9, and it is 4 away from 16, so it's about halfway between. And that means that it's going to be about halfway between the square roots as well. So the square root of 9 is 3, square root of 16 is 4. I'm going to guess that the square root of 12 is about halfway between 3 and 4, so I'm going to guess 3.5. Now I need to check my guess by multiplying 3.5 by itself or squaring it. I should get an answer that's within 0.5 of 12. So 5 times 5 is 25. 5 times 3 is 15, plus 2 is 17. Placeholder 0 as I switch places. 3 times 5 is 15. 3 times 3 is 9, plus 1 is 10. Adding those up together, we've got our 5, 2, 2, 1, and 2 digits in decimal places. So this one is only off by 0.25, so that is within 0.5 of 12, so that was a pretty good guess. Since that is a little bit too big, it's more than 12 obviously, we could check our 3.4, reducing our guess since our result was too big, and see if that gives us a number closer to 12. So 4 times 4 is 16, 4 times 3 is 12, plus 1 is 13, Placeholder 0, 3 times 4 is 12, 3 times 3 is 9, plus 1 is 10. So that one is further off, right? It's off by 0.46. It's obviously still within 0.5 of 12, but it's further off than our first guess. And so what we want to do is say that our square root of 12 is approximately equal to our first guess, which was 3.5. Now again, we're going to say approximately equal here because we know that this square root of a non-perfect square is really a non-terminating, non-repeating decimal. So it's not going to be exactly 3.5, but to one decimal place to the nearest tenth is a good guess that it is about 3.5. Okay, same idea for 170. So let's think about our perfect squares that are around 170. Square root of 169 is 13, and square root of 196 is 14. Since 170 is very, very, very close to 169, it's only 1 away from that, and it is 26 away from 196. We're going to guess that it's very close to 13. So we're going to check 13.1. So 1 times 1 is 1. 1 times 3 is 3. 1 times 1 is 1. Placeholder 0. 3 times 1. 3 times 3. 3 times 1. Whoops. 2 placeholder zeros as I'm 2 places over. 1 times 1. 1 times 3. 1 times 1. We got 1, 6, 11, 7, 1. 2 digits in decimal places. So this is off by 1.61. Whereas if we use just 13, we'd only be off by 1 from 170. So I'm going to say that square root of 170 is approximately equal to 13.0. That's our best guess. It's obviously not exactly 13. It would be a little bit more, but to one decimal place, 13 is our best guess. Question C, closest perfect squares around 72. The smaller one is 64, whose square root is 8, and the larger one is 81, whose square root is 9. 72 is 8 away from 64, and it is 9 away from 81. So again, we're about halfway between those two. So we're going to guess, I don't know, 8.5. Again, let's long multiply to check. So 5 times 5 is 25. Whoops, 5 carry 2. 5 times 8 is 40, plus 2 is 42. Placeholder 0, 8 times 5 is 40. 8 times 8 is 64, plus 4 is 68. Add them up. So that is 72.25, and that is close enough. So we're going to say that our square root of 72 is approximately equal to 8.5. Okay, last one here. Let's think about this a little bit. This is obviously outside of our memorized range, but we do know that square root 400 is equal to 20 from our tens. So let's think about 21. 1 times 1 is 1, 1 times 2, 2 times 1, 2 times 2. So that's going to be pretty close to 450. So I'm going to say that the square root of 441 is our smaller perfect square. And that means our next largest perfect square will be whatever 22 times 22 is. Nice easy calculation. 484. So 450 is obviously 9 away from 441, and it is 34 away from 484. So we're much closer to 21 than we are to 22. I'm going to guess, let's say 21.3, let's say. About a third of the way, or a third as much towards 450. So when we long multiply out 21.3 times itself, 3 times 3 is 9, 3 times 1 is 3, 3 times 2 is 6, 1 times 3, 1 times 1, 1 times 2, 2 times 3, 2 times 1, and 2 times 2. and that gives me 453.69. So that was actually too much, right? We're off by 3.69 from our desired 450. So we're going to re-guess, and 21.2 times 21.2 is our re-guess. 2 times 2 is 4, 2 times 1 is 2, 2 times 2 is 4, 1 times 2, 1 times 1, 1 times 2, 2 times 2, 2 times 1, 2 times 2. 4, 4, 9, 4, 4. So that is obviously closer to our desired 450. And we'll say our square root of 450 is approximately equal to 21.2. And again, in all of these cases, if your first guess is too far off, adjust it. So if your guess gives you a multiplication that's too high, reduce your guess. If your guess gives you a multiplication that's too low, increase your guess. There you go. Okay. Is each of the following true or false? Explain your answer. Square root of 19 is between 9 and 10. Well, square root 19 will be between square root 16 and square root 25. Square root 16 is 4, and square root 25 is 5, so that is going to be false. It should be between 4 and 5, not 9 and 10. The misconception that one's getting at is that people think a square root is dividing by 2, and that is obviously incorrect. That's not what a square root means, so that one there is false. Question B, we got to think about a little bit. So it says the square root of 7 multiplied by the square root of 7 produces or equals 7. So how could we check if that one's true or not? Well, we do know that a number multiplied by itself, so we got a number inside the brackets here, multiplied by the exact same number inside the brackets, can be written as that number squared. And what do we know happens with a square and a square root? They cancel out. So canceling the square and the square root leaves us with just 7, and 7 is equal to 7, so that one is true as well, using that knowledge of a square and that it cancels with our square root. Last one here is a bit of a unique one in terms of we got 11 unique factors, so that number could not be a perfect square. So let's think about an example here. Let's, for example, think about 36. Now the factors of 36, just pairs of numbers that multiply to make 36, are 1 and 36. We have 2 and 18. 3 and 12 multiply to make 36, 4 and 9 multiply to make 36, and then 6 multiplies by itself. So in terms of unique factors, it just goes right in the middle. And we do know that the square root of 36 is 6. So in terms of how many factors we have 1, 2, 3, 4, 5, 6, 7, 8, 9 unique factors. And it turns out that anytime you have an odd number of unique factors, means that it must be a perfect square. Because it means that there's going to be that number in the middle that's being multiplied by itself. That's the only way you would get an odd amount of factors, is to have that number multiplied by itself in the middle. And so that's going to mean that it is a perfect square, not that it is not. It's kind of more of a niche definition of perfect squares, so I wouldn't worry too much about that one if you weren't sure about it. But it is one way or one other way of checking if something's a perfect square. Now we should again mention that these are for factor pairs, not for the prime factors. Again, prime factors, 2 equal groups is our main idea. Last ones are problem-solving questions. These all deal with the idea that a square and its side length in a situation, and then doing different things with that side length. So our square floor has an area of 625, and we know that area is going to be the perfect square. We want to find the length of one side, which we know from our definition is our square root. So we're going to say our side length is equal to the square root of 625. Again, if you weren't sure about what that is, you could break that down into its prime factors. 5 goes into 6 one time, 5 goes into 12 2 times, 5 goes into 25 5 times. And so again, circling every second group, or every second factor I should say, to make 2 equal groups. we can say that S is equal to 5 times 5, which is 25, and our units there are meters, since the meters squared has been square rooted, leaving us with just meters. So our side length of the square is 25 meters. For our perimeter, we want the total side length around the outside. So in terms of our square, it's a lovely square there. We've got 25 meters on each edge. We want the total of that. So our perimeter is going to be 4 times 25 meters, which is 100 meters. Okay, so using some knowledge from grade 7 there, after we've used our grade 8 knowledge to figure out the side length. Question 9, same type of idea. We've got a square rug with an area of 144 meters squared. We want to center that in a rectangular room that measures 14 by 18. So let's go ahead and draw ourselves our room. So our shorter side is 14, our longer side is 18. And then in that room we have this rug with an area of 144. And that means that the side length of the rug is the square root of 144. Square root of 144 is what number multiplies by itself to make 144, which is 12. So we know that this side here is 12, and this side here is 12 as well. Okay, so in order for that to be centered, we want an equal distance on either side of the rug in both dimension. So if we think about our kind of vertical in our drawing, I guess that is in red, our extra distance is going to be the 14 of the room, take away the 12 of the rug is 2 meters. Then we're going to split equally to top and bottom. So it's going to be 1 meter from the top and 1 meter from the bottom. For our horizontal distance, our extra, or our difference that needs to be centered, it's going to be 18, take away the side length of 12, or 6 meters. Then we want to split that equally as well. So we're going to divide that by 2 to get 3 meters on either side. And if we just check vertically, 1 plus 12 is 13, plus 1 is 14, and that is the overall distance of the room. And horizontally, 3 plus 12 is 15, plus 3 is 18, and that is the horizontal distance of the room. Since it's centered, or it's an equal distance top and bottom, it is centered. So we're going to say 1 meter from the top or bottom, and we're going to say 3 meters from left or right in my drawing. Okay, in terms of our last one, we want to find the total perimeter of the shape. We know that the distance around the side of these shapes would be the square root of their area. So square root 256, what number multiplies by itself to make 256 is 16. Square root of 169 is 13. 13 multiplies by itself to make 169. Now we do need to deal with this little piece here. We do know that the total length of this whole thing is 16. And we know that this length is 13. So what's the difference there? This little piece is going to be 16. Take away 13, the difference, which is 3 meters. So we could say our perimeter is equal to all our measurements added up. We've got 16 plus 16 plus 16 for these guys there. Then we've got 13 and 13 and 13. And then we've got our extra 3. Okay, so 16 plus 16 plus 16, or 16 times 3 is 48. 13 times 3 is 39. And then adding those together, 48 plus 39, well, 48 plus 30 is 78, plus another 9 is 87. And then we've got our plus 3, gives us 90 meters around the outside. Okay, so I hope that's helped you with your squares and roots readiness guide.